Hi, I'm Michael Osman of Great Scott Gadgets, and this is Software Defined Radio with HackRF. Lesson 11, Replay. In this lesson, I will give a demonstration of how a captured radio signal can be replayed or retransmitted with Software Defined Radio. But before I start transmitting, I'd like to say a few words about being a good neighbor on the spectrum. Your country probably has laws governing the transmission of radio signals, and those laws are likely more restrictive than any rules about receiving radio signals. If you'd like to know more about the rules in your area, I recommend pursuing an amateur radio license. In the process of studying for your license, you'll learn a lot about rules that you're subject to, and when you gain your license, you'll gain privilege to transmit on certain frequencies. There's one thing that all of these rules have in common across all countries that I know of, and that is a common goal of sharing the radio spectrum among many different people. The radio spectrum is inherently a shared resource, and so it's important that we are able to use the spectrum without interfering with other users of the spectrum. That's the reason why we have most of these laws. So instead of talking about any particular laws, I'd like to talk about ways that you can be a better neighbor on the spectrum. If you're thinking about transmitting with software-defined radio, one of the things you should consider carefully is frequency of operation. If you're trying to emulate some device that you can legally operate, then emulate it as carefully as possible, and that includes operating on the exact frequency that it operates on. If you're not emulating any particular device, but are just doing some general purpose experimentation that could happen on a wide variety of frequencies, then try to pick a band that is an unlicensed band in your area. For example, ISM bands, or industrial, scientific, and medical bands. ISM bands such as the 2.4 gigahertz band are common in many countries throughout the world. And which particular bands are available in your area varies depending on country, but the 2.4 gigahertz band is one that exists in every country that I know of. The reason that you would use such a band is because it's unlicensed in that you are allowed to use equipment that operates in that band without you having a license yourself. There may be rules, however, about the authorization of the equipment, even though there aren't rules about the authorization of the user of the equipment. So we call those unlicensed bands, and one of the characteristics that those bands tend to have in common is that users of the unlicensed bands are required to tolerate other users of those bands. And that's very different than licensed spectrum, in which a user is given a particular license to operate some radio system on a particular frequency and has the expectation that no one else is using that frequency. So try to use those unlicensed bands anytime you possibly can, or emulate the particular frequency of operation of a device that you can legally operate. Another consideration that's related to that is the bandwidth. You've seen how software-defined radio receivers collect a range, collect a radio signals over a range of frequencies. And when you transmit with software-defined radio, you also transmit over a range of frequencies. So be careful of your bandwidth and be careful of neighboring frequencies and users of the spectrum, adjacent channels that may be within that bandwidth. And perhaps the most important thing you need to pay attention to is your transmit power, the output power of your transmitter. The number one thing you can do here is to simply use the least power that you need to accomplish what you're trying to accomplish. Don't start at high power and then scale it down. Start at low power and scale it up, and only scale it up to the point that you need. The power that really matters, of course, is how much power is received by other users of the spectrum. And so location can be important. You can, if you're able to do your experiment in a location that's far away from other users, then you're far less likely to interfere with them. And what you need to consider is the receivers of other radio systems, much more so than the transmitters. It's a common misconception that you can jam a transmission or jam a transmitter, but you don't really jam transmitters typically. Transmitters normally don't care too much or aren't affected much aren't affected by other radio signals that are in the area. But receivers can be greatly affected by radio signals that are in adjacent bands even, that happen at the same time, that can overpower their signal. For example, probably the easiest system to jam that you're familiar with is GPS. The GPS signal received by a receiver has come from such a great distance from a satellite that it is very, very weak, and it's extremely easy to jam a GPS receiver, deliberately or not. Of course, deliberate jamming is the worst thing you can do to be a good neighbor on the spectrum, and that's what we try to avoid when we're trying to be a good neighbor, is not just deliberate jamming, but any unintentional jamming that we might do. So keep in mind how much power you're transmitting that might be received by other radio receivers. One thing you can do is to operate inside a shielded enclosure. We call these Faraday cages. And a big Faraday cage that you can walk into is extremely expensive, but they can be built yourself, and smaller tabletop units can be built yourself. I know some people who use discarded microwave ovens, which are intended to shield 2.4 gigahertz radio signals. So that could be a good option for a do-it-yourself Faraday cage. Operating in a basement, for example, is one way to attenuate your signal before it reaches other users who are outside your basement or who are above ground. Anything you can do to limit the power of operation or the power received by other users is a good thing. And the easiest place to start is by simply having your software-defined radio transmitter configured to transmit at the lowest power that you need. One way to minimize the amount needed is to simply do things at very close range. If you need to transmit a signal from one device to another and you have them centimeters away from each other, then you can probably transmit at a much lower power than you could if that device were in the next room, for example. So have your transmitter and your receiver as close together as possible. Of course, the closest they could be is to actually be connected. And this is a great option in a lot of scenarios. That is to connect your transmitter to your receiver over a cable. A coaxial radio cable is actually a shielded enclosure. It has a shield around a piece of wire that goes through it. Now, if you do connect, say, a HackRF to another HackRF directly, you have to be careful that you don't overpower the receiver. The transmit power is higher than the maximum safe receive power. So what you can do is get one of these little attenuators that can be connected in line with the cable and gives you the ability. This one is a 20 or 30 dB attenuator, and I would recommend using a minimum of 20 dB of attenuation. And it's kind of similar then to operating over the air inside a shielded enclosure. When you transmit over the air, going any distance over the air attenuates the signal quite a bit. I usually think as a rule of thumb that it's something like 30 dB of attenuation. That's the distance. That's the difference between having two antennas that are touching versus two antennas that are almost touching. Just going over a little bit of air gives you maybe 30 dB of attenuation. So if you can put 30 dB of attenuation onto your cable and connect the two devices together, then you emulate what would happen over the air. and that cable is shielded and prevents you from radiating that signal really at all to any measurable extent that anyone would care about. So another thing you can keep in mind, in addition to using an attenuator on a cable, is that you could use a dummy load. These are little connectors. They look just like the connector that's on the end of a cable, except they have no cable attached. And you screw that on to your transmitter, and it provides a load, meaning that the transmitting device operates as if it had an antenna. It is safe to operate, although sometimes it might be unsafe to operate transmitters without an antenna attached. You can put a dummy load on, and it makes that device safe to transmit, but most of the radio energy gets absorbed in that dummy load instead of being radiated out over an antenna. And that's a good option that you can use if you need to do something over the air, but want to do it at very close range and at as low power as possible. Put a dummy load on your HackRF or other transmitter, and at very close range, you should still be able to pick up just enough of a radio signal to accomplish some experiment. And perhaps the most important thing you can do is to be a good neighbor on the spectrum is to verify that you're transmitting what you think you're transmitting. If you use some test equipment like a spectrum analyzer, or you could even use another software-defined radio platform, you'll be able to measure your output, measure what you're transmitting, ensure that you're on the frequency you think you are. You can check and see that your signal looks like you think it should, and ensure that you're operating over the correct period of time and over the correct frequency and correct bandwidth and correct power levels and so forth. It's something you have to be very careful of with software-defined radio platforms. The general purpose software-defined radio platforms, such as HackRF, may produce output on frequencies that you aren't expecting. Of course, most of the energy should be at the frequency that you've configured it to, but there may be weaker signals, images, or spurs at other frequencies that you weren't expecting. And so those should be weaker, but you can measure those with another software-defined radio platform or with a spectrum analyzer. I mentioned time briefly, and something you can do that's very easy to minimize your potential of interfering with other people is to minimize the amount of time that you transmit. If you only need to transmit for a second, don't transmit for an hour. It's as simple as that. The less time you spend transmitting, the lower the probability is that you'll interfere with any other users. And another thing you might consider if you're thinking of transmitting is amplification. You might be thinking about attaching an external amplifier to software-defined radio platform. Don't do it. If you can possibly avoid it, don't amplify. Don't connect these things to external amplifiers. And if you are tempted to do so, you need to be very careful about the laws. You need to be very careful about everything I've talked about, especially verification and bandwidth. You need to consider those images and spurs that might happen on other frequencies, and so you'll almost certainly need to use a band pass filter, an analog band pass filter that you can put in line between your software-defined radio platform and your amplifier to make sure that you're not amplifying signals at unintended frequencies. But if you can possibly avoid using amplification, do so. One thing you can do to avoid amplification, of course, is to move closer to your target. If your transmitter and your receiver are closer together, you'll have much less need to amplify. Another thing you can do is to use the best antenna you can for the job. If you use a directional antenna and you use a high gain directional antenna, you can likely transmit a signal that will be at significantly higher power at your target receiver without interfering so much with any other receivers that might be in the area. So that's a way that you could avoid having to amplify, is simply by moving closer and using a better antenna. So try those things first. Don't amplify unless it's a last resort. And if you need that external amplification, be very, very careful about all these things, and in particular pay attention to the laws in your area. Now, I'd like to go ahead and give you a demonstration of a capture and replay. And the device that I'm going to use is, the target device, is this radio-controlled car. So I'm going to give it a signal from its original transmitter, and we will capture that signal and then see if we can replay it and make the car respond. Before we can replay a signal, we have to capture it. So I'll start by making a flow graph to receive a signal from the remote control. I'll use a source, an Osmocom source, and I will, to start with, just visualize the signal and see how it goes. And I'd like to use an FFT sync, but this time I think instead of using a WX GUI FFT sync, I'm going to use the QT GUI frequency sync. Now the frequency sync gives you a frequency domain plot, so it's very similar to the WX GUI FFT sync, except it's using the QT GUI widgets instead of using the WX GUI widgets. It's just a different library, a different set of tools that you can use. However, you have to be very careful when you're dealing with these things. And the reason I'm selecting QT right now is because this default over here in the generate options has changed in GNU Radio in recent months. And I'm using a newer version now, and I noticed that it is the default. So I thought I should use it in my videos, although I do still like the WX GUI elements for some things. For this particular video, and probably most of mine going forward, QT will be fine. So if I connect these together, you should see that my flow graph is happy. But let me show you what happens here if I were to take one of these WX GUI elements and connect it into my flow graph. Notice that it is unhappy. It has a red title here. Even if I disable my other QT GUI element, I have a WX GUI element, and nothing is going to happen. It doesn't give me the opportunity to generate a Python program or execute it. And the reason is because the WX GUI element is in my flow graph, even though my options say to generate a QT GUI. You can only have one, not both toolkits. So if I go into my options properties, I can change this, the generate options pull down. I can change it between QT GUI and WX GUI. If I change it to WX, now my flow graph is happy. So you have to have your entire flow graph be either QT or WX. Whichever one you want to use is fine for now, but going forward, the QT GUI elements will probably be better supported and have more active development in the future. But it's a fairly recent change, just this year, to change the default in GNU Radio Companion from WX to QT. Now, I said I'd like to use QT this time, so I'm going to re-enable this QT GUI sync and get rid of my WX FFT sync, but that means, of course, I have to go back and change my options. I'll go in here in the options block and set the generate options to QT GUI, and now everything should work just fine. So let's run this and see what happens. Oh, wait a minute. I have some things I need to set, don't I, in this Osmocom source. First of all, I need to set a sample rate. I will use a sample rate of 2E6, 2 million samples per second, which is the lowest sample rate I ever recommend anyone use with HackRF1. And then I'll go into my Osmocom source, and I need to set a frequency. I'll set the frequency to 27 megahertz, and the reason I'm choosing 27 megahertz is because the toy has a sticker on it that says 27 megahertz. And of course I like to set my RF gain to 0, and why don't we start with 16 for my baseband gain and intermediate frequency gain. It's a good starting point. Now let's see what happens. I'll execute this flow graph. I'll give it a name. And here we have an FFT running in real time. One thing you'll notice that's different between the WX GUI FFT sync and the QT GUI frequency sync is that the QT GUI does not have some of the controls that you're used to on the right-hand side. But if you use your third mouse button or your middle mouse button, you can bring up a menu that has a whole bunch of different options, including things like max hold that we've used with the WX GUI FFT sync. So let me try max hold, and I'll pick up my remote control for the toy and try to move the car a little bit and see what happens. Hey, look at that. I'm definitely getting a signal, and I can move it forward or backwards or left or right, and I always see that peak a little bit to the right of 27 megahertz. It looks like it's about 150 kilohertz above 27 megahertz there. So we've definitely found the signal, we're picking it up, and now I'd like to save this waveform so that I can replay it later. How are we going to do that? Let me close this flow graph and add something to my flow graph here. I don't need to add any more instrumentation. What I need to add is saving the data to a file. So I'm going to use a file sync. It's under file operators. And the regular file sync, you'll notice, has a default data type of complex. So all I have to do is plug that into my source. And I do want to give it a file name. So I'll go into the properties and call a file, let's say /temp/car. And sometimes you might want to add some information to your file name. For example, the sample rate and the frequency of capture, maybe other settings. But for now, I'll just call it /temp/car. And at this point, I could even remove or disable the frequency sync, but I like to be able to visualize things while the flow graph is running. So I'll leave that enabled. So I'll be visualizing the signal with an FFT and at the same time saving the waveform to disk. Now this is the raw digital waveform. It's the information coming from the HackRF being saved directly to a file. I'm not demodulating it, I'm not filtering it, I'm not doing any kind of processing whatsoever. I'm just taking the data from the HackRF and sending it to a file. Let's see what happens this time. Should look exactly the same, but we should end up with a file at the end. So here's my FFT, and then I make the car go forward a couple times, and I waggle its wheels side to side a little bit with the steering, and then close my flow graph. And now I should have a file called /temp/car. So let's take a look at that. I'll go into my /temp directory and look at this file. Here it is. It is how many bytes long? 161 million bytes long. It's a pretty big file. And this is something that you'll find happens when you use this technique. Realize that I was capturing it only 2 million samples per second, which is the minimum sample rate that I recommend with HackRF. And just capturing for a short period of time, I got a file that was 160 megabytes. Really a lot of data in a short period of time. Why is that? Well, let's take a look at this file. I'll just use XXD to do a hex dump for a moment. And you can see, do you see how much redundant information is in this file? See how there's a 0 byte and then a 0 byte and then these 2 bytes and then a 0 byte and a 0 byte and these 2 bytes. There's a lot of zeros in here. And the reason you see this pattern that goes 4 bytes long is because what we are saving is the complex data type, the blue data type here, which is complex valued. And that is a pair of floats for every sample. A floating point number is is 32 bits long, or 4 bytes long. So what we have here is one floating point number for I, and then another floating point number for Q, and then the next floating point number for I, and floating point number for Q. And there will be a limited number of values used here, even though it's 32 bits, well really 64 bits for a single quadrature sample. There will be a limited number of values that we see because these have been converted from 8-bit signed integers that came over the USB cable. They've been converted from 8-bit integers into 32-bit floats. So this file it grows quite quickly because there are 2 million samples per second, and there are 2 values in every sample, and there are 4 bytes in every one of those floating point values. If we use a different tool, like I like the OD command, which is, I believe stands for octal dump, but I'm going to use it with the floating point option. If I look at the file this way, I can actually dump out the floating point values. And if I were to use, I think it's W4, which is, W8, which is going to be interpreting 8 bytes at a time, a width of 8 bytes on every line. Here I get I and Q, and then that line is repeated. And then I get an I value and a Q value, and an I and a Q, and an I and a Q. So I get one sample per line. And I could turn off these stars for repetition if I wanted to. But this gives me an idea of the values that are in this waveform. And we'll probably see different values if we were to look further down the waveform to where there was actually a signal being picked up. But I'm just checking what this file looks like just for fun and to show you what's in there. I don't really want to analyze it using this method because it would take quite a while. It's 160 million bytes to analyze. But this demonstrates, it shows that we have this file called car, and is a capture of my remote control while I was trying to drive the car a little bit. Now let's try to do something with that file in GNU Radio Companion. I'll start a new flow graph, and this time instead of using a file sync, I'll use a file source. And I'll point that file source to the file /temp/car. Of course, the first thing I like to do is visualize things, or instrument my flow graph. I'll again use a Qt GUI frequency sync, and I could plug that straight into my frequency source and run this flow graph. However, I probably want to slow it down with a throttle block so that I don't crush my CPU. Under miscellaneous, grab a throttle, and now I have a flow graph that should make sense, but for the rulers to be correct on the frequency and for it to perform in the same speed as real time, I should go in and set my sample rate to be the same sample rate that I used for the capture, which was 2 million samples per second. We'll give this flow graph a name. And here we have a GUI FFT sync, and there's our signal, 150 kilohertz above center. If I use my third mouse button and set max hold, then we can see that it's consistently at that same frequency. Now, one thing you might notice here is that this is going on for a period of time that is actually longer than my original capture. And the reason for that is that the default setting for a file source is, if we look here, repeat yes. So this flow graph will run forever, repeating that same input. We could change that to no, and if we do that, then the flow graph will only run until it runs out of input in that file. But since I've set it to repeat, which is the default for the file source, then I get to see the same thing over and over again. And sometimes that's what you want, and sometimes it's not. But it's good to know that that's the default. Let's take a look at what we can do with this now. What do you think we should do if we want to replay this file? Well, I think what we could do is simply deliver this from the file source, deliver this waveform to an Osmocom sync. And I don't think we've used an Osmocom sync before, but it shouldn't be much of a surprise that such a thing exists. If you compare it to the Osmocom source, you'll see that they're very similar. They have some of the same characteristics, except one of them is used to receive a signal from a software-defined radio peripheral and deliver it to your flow graph as an output. And the other one is designed to take input from your flow graph and deliver it to the HackRF or other software-defined radio peripheral. So I'm going to delete my source here. All I need is the sync. Or let's just delete it, not just disable it. And I could plug in this sync into my throttle block, but then I would have a 2 clock problem, because my HackRF is inherently clock limited already based on the speed that I tell it to go in terms of samples per second. And what I should do is, in fact, connect this directly to the source. The source directly to the sync. It doesn't need to be throttled, and it shouldn't be throttled because it's inherently rate limited. But I should take care with the other settings. Let me take a look and see here. This should be 27 megahertz because that's the same frequency that I used to capture. Now remember that the signal of interest is actually at 27.15 approximately megahertz. But it's a little bit above. It's 150 kilohertz above that center frequency of 27 megahertz in our capture file. If I want to replay it and have it remain 150 kilohertz above 27 megahertz, then I need to have my center frequency exactly the same for my replay as it was in my original capture. Of course, I like to set my RF gain to 0, and these values are actually a little bit different in when we're in a transmit mode. The IF gain is something that affects the transmitter, but the baseband gain actually makes no difference whatsoever because there is no baseband amplifier in the transmit path of HackRF. There is a baseband amplifier on the receive path of HackRF1, but not in the transmit path. So it doesn't really matter what we type here. It does matter what we type here and here. I'll just leave it with the default of 20, and which is roughly in the midpoint of the gain range, and I'll leave the RF gain off for now. Now, will this work? One thing I notice is that I do have 2 clocks in this flow graph, and this might work actually, but I could disable my throttle block and connect this directly to my frequency sync, and this should work fine because the frequency sync isn't going to go any faster than the Osmocom sync. They're both going to be pulling from the same file source, so the data will flow at the same rate to both of them. So this works like this with only 1 clock in my flow graph, and that's the clock in the HackRF that is here through the Osmocom sync. So at this point, I should be able to execute this flow graph and replay this signal, transmit it over the air to my remote controlled car, and see if it actually moves the car. I'm going to hold the car up and run the flow graph and see if I can get the wheels to move. So I start my flow graph, and it's starting up, and here comes the signal. It's transmitting, but the wheels aren't moving. And I suspect this is because I'm simply not transmitting at high enough power. So let me try increasing the power a little bit. Actually, let's try increasing the power quite a bit. If I go into my Osmocom sync and look at the properties, the maximum value that I can use for the IF gain is 47 decibels. That's 27 decibels higher than I had it set before. Let's just try that and see what happens. The signal's transmitting, and yet still the car's wheels aren't moving. Let's investigate what's going on a little bit more closely. One of the benefits of having a saved waveform like this is that we have a consistent test vector. I'm not recapturing the original transmitter every time I run a flow graph and possibly introducing different problems depending on how I'm holding things or different changes in my environment like interference. Everything should be the same every time I read data out of this waveform. So let's take a look at what is in this waveform a little bit more in more detail. One of the tools I like to use when I'm working with a file like this is a new piece of software called Inspectrum. And if I type Inspectrum -R 2E6, it knows how to parse sample rates like that. I give it a sample rate and I give it my file name, and it brings up what is called a spectrogram. Let me increase the size of this window a little bit so you can see more of what's going on. This spectrogram is a two-dimensional picture of the information that is saved in that file. What we have is time on the vertical axis and frequency on the horizontal axis. Let me scroll down a little bit until we see something going on. Here we go. You can see that bright line down the middle. That corresponds to the spike that we get at 0 Hertz in the center of our FFT sync in GNU Radio Companion. And then we see things happening a little bit above center, just like we did in the FFT sync in GNU Radio Companion. And I can change things like the FFT size, which affects the width of the analysis. And I can change the zoom, which affects the height. Look at that. I can also change the color scheme depending on basically setting thresholds of which colors are applied to which power levels. And if I adjust things like so, you can see that it really pops out at me what kind of waveform this is. The frequency is very consistent because everything falls in this vertical line. But the power level goes on and off very dramatically. This is, if I scroll around to the beginning, you can see this is the beginning of on-off keying. Now it's pretty cool that we can see that just by looking at the waveform with this tool. But we don't actually need to know what type of modulation it is, theoretically, in order to do this replay exercise. We don't have to decode this information. We don't have to understand its modulation at all. We just have to have a capture that fully contains the signal that we're interested in. And we seem to have that. If I scroll up, you can see there's a bunch of time here where nothing happens. And then I have my signal. And then there's another burst and another burst, and these probably correspond to different times that I moved the control sticks on the remote control. And then at the end, there's some empty time after I have transmitted anything. So I have some emptiness at the beginning, some emptiness at the end, and a very clear on-off keying signal right down a consistent frequency just above my center frequency. Now, this is useful perhaps, but it isn't really showing me what might be wrong with my signal. And I suspect what might be wrong is actually the power level. Do you notice, if I turn up my power max here, do you see how it turns red almost the same point at which this spike in the middle turns red? That indicates that my power level, the power level of this received signal, is only approximately the power level of this defect here. And that is a little bit troubling. Let me take a closer look in GNU Radio Companion. If I perhaps use something other than just a frequency sync, let's try and instrument our flow graph with a time sync, which is a time domain plot. So this is very similar to a scope sync in the WX GUI options. There's a WX GUI scope sync that gives us a time domain view, like an oscilloscope. But I'm going to use the Qt GUI time sync, which gives us a time domain view using the Qt GUI options. And I'm going to run it through my throttle block and turn on my throttle block and turn off my Osmocom sync for now. And I'm repeating this file and running it through these sinks to see what I get. Okay, so now I have my FFT on the bottom and my scope plot above. Okay, do you see how that looks now in the time domain? In between bursts of activity, I get this very low valued signal, very close to 0. And then during bursts of activity, you see something that looks sinusoidal. Now, if I were to zoom in a little bit, and one of the ways you can do that using this QT plot is by dragging a rectangular area within here. If I want to just zoom in, I can just choose an area to zoom in to and see what I get. There we go. Now I'm going to middle click and select stop, and that will pause the flow. It doesn't pause the flow graph, it just pauses this view. And inspect a little bit this background noise here that happens between bursts of activity. Do you see how everything's between 0 and negative 0.1? It's offset from 0 a little bit, which is no big deal, but that's an explanation and we'll talk about this later a little bit more detail perhaps, but that's an explanation for this 0 hertz spike in the middle. There's some portion of the signal all the time that is a little bit off from 0. Now, that's perfectly normal in a receiver like HackRF to produce that type of a small defect. If I restart here and then try to stop it, oh, I missed. I'm not doing a very good job here. If I try to stop it when there is actually a signal present, you can see that the signal itself is also fairly weak. It isn't a whole lot bigger than a greater amplitude than the background noise between bursts of activity. The background noise was kind of between 0 and negative 0.1. And this activity, the actual burst of a transmission, is only ranging between, about 0.1 and negative 0.15 in amplitude. And one of the things I like to do with the time sync is use a stem plot. And this is similar to using the dot large option in the WX GUI scope sync. It gives me a dot, a bold dot for every sample, and then it has a vertical stem that extends to 0. And if I zoom in on this a little bit more, you can see the pattern of activity here. Notice that these are only extending about 0.1. The amplitude is fairly small if you think of amplitude being, let's say, maximum amplitude should be between negative 1 and positive 1. That's the scale that we expect, because when the Osmocom source receives information from the HackRF, it takes these 8-bit values and then scales them and assigns them floating point values that are between negative 1 and 1. In other words, we're using a very small portion of our dynamic range. How much vertical scale we have available to us is from negative 1 to 1. But how much are we using? Only about 1/10 of that. And if I zoom in, you can actually start to see a little bit that these have sort of distinct values. There are only so many different values that are getting used. And this is even more apparent probably if we look at the background noise between packets. Do you see how these blue dots are all at the same value? Well, except for one here. And these red dots are mostly at the same value, a couple that are a little bit different. There are just a few very distinct values that are being that have samples assigned to them. So you can actually see, and if we were to scale these up by 256, you would see that these are integers. So for example, this might be 0, and this might be a negative 1, and then this dot would be at negative 2, and so forth, something like that. What we're seeing is that very little of our dynamic range is being used. And we could actually amplify our signal in the digital domain. Let's think about how we would do that. How would you make a signal stronger in the digital domain? Before we even take this waveform and give it to the HackRF, can we scale these values up? Sure we can. We can scale samples by multiplying them. So I'm going to close this flow graph and institute a new block in my flow graph. I'm going to use a math operator, multiply const. And if I put a multiply const into my flow graph, let's say I put it just before the throttle here. If I were to set the constant to 1, then that should have no effect. I'd be multiplying every sample by 1. But what if I multiply everything by, say, 6? Let's see what happens. Things look pretty much the same, except notice that the FFT sync, everything has shifted up a bit, and in our scope plot we can see that the sample values are in fact extending from about 0.5 to -1. If we were to remove the DC offset or just shift it up a little bit, we could even gain a little bit more dynamic range, but not a whole lot. Now we're using most of the full scale that is available to us. And I want you to realize what happens here. When we were looking at the sample values using the OD command, like so, you see how all of these values are close to 0, but there's only certain ones because they were converted from signed 8-bit integers. They were divided by 127 or 128, and so they were scaled into numbers between 0 and numbers between 1 and -1. And so there were only so many of these values that get used, and that's why you see a lot of repetition in this file, a lot of the same value over and over again, because they're small integers. And if we have, let's say, only 4 different values being used, then that means we're really only using 2 bits of our dynamic range. We have 8-bit samples, but the high 6 bits are always set to 0. So we're not using very much of our dynamic range. We can use more of our dynamic range when we transmit this file if we are to multiply it like we are here. And this is a way that we can amplify our signal in the digital domain before converting it to the analog domain. Now let's see what happens if we transmit this file with our flow graph with the multiply const through the HackRF. All I have to do is re-enable my Osmocom sync here, and I'll run it, connect it to the output of the multiply const. Let's launch this flow graph and see what happens. The flow graph is active, and it should be transmitting its signal very soon. There it is! It's moving the wheels. And if I leave the flow graph running, it will repeat the same thing over and over again. But I don't think I should leave it running for very long, because I don't think I'm being as good a neighbor on the spectrum as I could be. One of the best ways to ensure that we're being a good neighbor on the spectrum is to verify what we're transmitting by using a receiver at the same time as we transmit. So I have a second HackRF1 plugged in, and I can actually add into my flow graph an independent graph here. I'm going to make an Osmocom source, and I'll plug that into my FFT sync, or my frequency domain plot. Notice that this is isolated. It's separate from the main part of my flow graph. And I might as well turn off the time sync here. All I want to do is view over the air what was transmitted. It's going to go from the file source into this multiply const block, then out the HackRF, the first HackRF using the Osmocom sync, and then it's going to go over the air, and this independent part of the flow graph is going to tune the other HackRF to a frequency that allows it to pick up the transmission over the air and visualize it. So I do need to update this Osmocom source. It should of course have a frequency set. I could set it to 27 megahertz, but actually I think I'm going to set it to 26, and I'll show you why in a little bit. And of course I like to set the gain to 0, and maybe I'll use a little bit more IF and baseband gain. I'll set those to 24. This should work, except that I don't know if it's going to correctly select one HackRF for the sink and the other HackRF one for the source. So I'd like to go in and configure these explicitly to talk to specific devices. I'm using the hackrf info command to get information about both of the hackrf ones that I have connected to my computer. And you can see that they have separate serial numbers. I'm just going to take the last section of the first hackrf, and as long as that last section is unique compared to the last section of the other one, and that's all I need. And I'll go into my Osmocom source, or actually my Osmocom sync property, and set the device arguments field to hackrf equals serial number. That specifies that sync should use that particular hackrf1. And then I'll take the other serial number and paste that into my Osmocom source and tell this block to use explicitly the other hackrf1. There is one more thing I'd like to do before I execute this flow graph, and that's to increase the sample rate on my receiving hackrf1. I'd just like to cast a wider net and see what's going on. I'll set this to maybe sample rate times 4, which will be 8 million samples per second. And of course that means that the visible bandwidth of our frequency sink will change by 4 times as well. So I'll set those to 8 million samples per second, whereas my transmitter is only operating at 2 million samples per second. And let's execute this flow graph and see what we get. Now you can see this very distinct peak that is 1 megahertz above our center frequency, and then some other stuff happening 150 kilohertz above that. This is interesting. So we have our center spike, our DC offset, and this is basically a defect of the receiving hackrf right now. But we also see this spike 1 megahertz higher. That's actually the DC offset that was received by the hackrf, the first hackrf in the first place, and now we're retransmitting that spike. That's not very good, is it? This signal up here, 150 kilohertz higher, is actually the signal that we're intending to transmit. And then this spike 150 kilohertz below it is something that we shouldn't really be transmitting. And if we do a max hold here, you can see even more distinctly this mound. Do you see how the noise floor has a mound in the middle of it that kind of is about 2 megahertz wide? Well, that is the transmit bandwidth of our transmitting hackrf. And we've actually captured some background noise, and we're retransmitting it within that bandwidth. So not only are we transmitting this spike here that we shouldn't be, we're also transmitting a bunch of broadband noise. It's not very powerful, but it's noise that we shouldn't be transmitting if what we're interested in transmitting is this signal that's right here at 1.15 megahertz above our tuned frequency. So what can we do to be a better neighbor on the spectrum? The first thing that I would think of is to filter, and just filter out this signal of interest before we transmit it. Let's give that a try. Sometimes I like to use a low-pass filter. I'll center a frequency at 0, I'll center a signal at 0 hertz, and then use a low-pass filter. But this time, just for expediency, I'll use a band-pass filter with complex taps so that I can specify a positive frequency without also specifying its mirror image negative frequency. I'll set the low cutoff to 100 kilohertz, the high cutoff to 200 kilohertz, and the transition width to 50 kilohertz. This is maybe a bit wider than I need it, but I'll definitely grab that 150 kilohertz signal right in the middle there, in the middle of the passband, and that's what I'm interested in. So I'll connect this in between my multiply const and my Osmocom sync, and let's give this a go. Now things look a little bit cleaner. Do you see how we are in fact transmitting, if I use my max hold here, we are in fact transmitting that DC offset just a little bit, but it's very weak. And then we transmit a much stronger signal. That's the signal of interest that we're trying to transmit. And we're not transmitting that broadband noise anymore over 2 megahertz of bandwidth, although we are transmitting broadband noise over this 100 kilohertz of bandwidth right here. Even between bursts, between the intentional bursts, we are transmitting a little bit of noise. So we're definitely being a much better neighbor on the spectrum than we were, although it looks like there may be some ways that we could still be a better neighbor on the spectrum yet. One thing I noticed that we could do, just to simplify our flow graph a little bit, is that instead of multiplying by this constant here, we could just use the gain parameter in the band pass filter. And sometimes I like to do this and sometimes I don't. The reason I don't sometimes do this is because I like to keep blocks separate that have separate functions just to make them easier to read. But it would be more efficient probably if I put the gain of 6 in the bandpass filter and stopped using this multiply const block. So I'll just disable that and go straight from the file source to the bandpass filter. We should see that things look the same this way, exactly the same as they would with that separate multiply const block. Now, can you think of ways that we might be able to even be a better neighbor on the spectrum than this? One way I could think of would be to trim our capture so that we don't have a bunch of excess time between the intentional transmissions that we're looking at. Another thing would be to try to address this background noise that we have between. It happens actually during our intentional transmissions and between our intentional transmissions. And there's inherently always some background noise every time we capture something. But what is important here is the ratio between this intended transmission and the background noise, the noise that we're transmitting. And depending on the quality of our capture, that signal to noise ratio has been set at the time that we made that original capture. If we had a very weak capture, if we weren't using very much dynamic range, then we have a fairly poor signal to noise ratio, and that means when we transmit, we're going to be transmitting a higher proportion of noise than we maybe could be. But if we were to recapture our signal and do it in such a way that we use more of our dynamic range and have a better signal to noise ratio in our capture, then when we retransmit it, this noise here would be much lower in proportion to our transmitted signal. So we could be a better neighbor on the spectrum actually just by having a better capture in the first place. Of course, the very cleanest way we could possibly transmit this would be actually decoding the information that was transmitted and synthesizing our new waveform that is generated in our CPU without actually capturing any noise at all. That would be the absolute cleanest way we could accomplish this. But what we've done here is a simple capture and replay. It's not the absolute cleanest we could possibly do, but it's pretty good considering how easy it is to accomplish. Keep in mind that we didn't have to decode this signal. We didn't have to even understand what the modulation was. Even if we don't know what the modulation is, we could still capture a signal once we've identified it and then replay it and find out if that replay actually does anything. It's a pretty powerful tool to have in our toolbox, being able to replay a signal. It's useful for testing systems to see if they respond to a replayed packet, and it's also extremely useful to create as a means of creating a repeatable test vector that we can use using HackerF1 to produce a signal that then could be used to test some other system. For homework for this lesson, I'd like you to find your own toy or other simple radio device, something that is likely to be a waveform that could have some effect when replayed, and capture it yourself and do an analysis similar to the analysis that we did with the transmission for this car. I'd like you to look at things like how much dynamic range is being used, and I'd also like you to get to know the HackRF transfer utility in order to capture the waveform instead of just using GNU Radio Companion all the time. Go to greatscottgadgets.com/SDR and look for the homework assignment under Lesson 11. I hope I'll see you next time for Lesson 12.